well. Next up is Nikola Jajcay. I hope I said this correctly, from the Technical University in Berlin. And his talk is titled Towards a Large-Scale Model of Sleeping Brain, Sleep Spindles in Network Mass Models. Nikola, are you able to share your screen with us?
Yes, I hope so.
The stage is yours.
Thank you, Elenor, a lot for the introduction. I just want to share with you a few thoughts about how to model sleep spindles in network mass models, the work I've been doing for the last year. Let me start with the motivation. The main motivation for my work is memory consolidation, where according to the two-stage model of memory consolidation, the newly encoded episodic memories are stored in hippocampus during the day, which offers rapid storage, but unfortunately also sparse representation, which means that it has very poor generalization. Then it is thought that during the offline periods, which simply means when we are asleep, these memories are transferred to the neocortex for long-term storage, and this happens via interaction between three brain areas, and that is the neocortex, hippocampus, and thalamus. Each of these brain areas during sleep offer some canonical oscillation. For the neocortex, those are the slow oscillations around 1 hertz. The thalamus is generating sleep spindles around 12-13 hertz, and the hippocampus is generating sharp wave ripples. And when all of these three oscillations are somehow hierarchically nested, and then there is a memory replay from hippocampus to neocortex, and by this there is an information transfer. And the neocortex offers slow acquisition and is parametric, and it's very efficient in generalization. My main work was the study of slow oscillation and spindle interactions. For now, we will completely omit the hippocampus and sharp wave ripples. And there is also a secondary motivation, and that is we want to be able to somehow perturb our brain while we are sleeping and strengthen the interaction between slow oscillation and spindles, which should lead to better memory consolidation, especially in elder people. And that is important that the cortical model we are using is adapted to include perturbations via transcranial current simulation. A few words about the model. We are using two different models for two different brain areas, of course. The thalamus is conductance-based mass model with two populations. The TCR stands for thalamocortical relay neurons. It is excitatory population, and TRN stands for thalamic reticular nuclei, which is inhibitory population. Since it's conductance-based model, our main variable is the firing rate, which is a simple monotonic transfer function. And then, of course, the average membrane potential is evolving according to Hodgkin-Huxley-like dynamics, where we have intrinsic currents important for thalamus, which are the rectifying current, calcium current, and potassium leak currents. For the cortex, we chose the adaptive exponential integrate and fire neurons, but their mean field approximation. So it's also a population model, and it includes the current mediating spike frequency adaptation. We can somehow evaluate our model in three different levels, as I like to call it. In first level, we just have the isolated thalamus and study just the isolated thalamus. In the second level, we have our cortex driving the thalamus, but there is no feedback connection. And in the third level, we have the full thalamocortical loop. I will briefly go through all of these levels because each of these levels can bring some knowledge to us. So in the first level, we have the isolated thalamus, and in my work, I'm in general, I in general study how the full dynamic landscape looks like. That means you have your model and you try all of the parameters, all of the inputs, everything, and you see how the model behaves in different settings. So the thalamus is parameterized via the conductances, since it's conductance-based model. We have two conductances that are important for spindle generation. And here in these plots, the color codes the spindle density. So meaning we have the isolated thalamus and how many spindles we have. And we were able to find in the noise loss case three different regions in which the thalamus is making spindles, and then we crank up the noise because of course the brain is noisy, at least when we model it. And only two of these regions somehow survived. And of course we have a lot of purely noise-induced spindles around with some low numbers, but in general these two regions really survived. And then we did the same for the isolated cortex. And the parameterization here is not via conductances because it's a different model, but we parameterize it via input currents to both excitatory and inhibitory masses. And what is important here is this upper limit cycle, LCAE, which stands for limit cycle between adaptation and excitation. That is why it's important our model actually have some spike frequency adaptation. And this limit cycle is actually the slow oscillations. If the cortex is parameterized in this regime, it produces slow oscillations around 1 or 2 hertz. Now let's go forward and let's connect these two modules. So the thalamus is parameterized in the noise spindles regime. The cortex is parameterized mainly in the adaptation excitation limit cycle. And what we've done here is something like a 3-dimensional landscape. And of course, it's hard to plot the 3-dimensional landscape. So for each pair of dimensions, I do 2D projections. This is how it looks like. What is important here is this plot in the last row middle column, because this is the same parameterization as in the last slide. So the inputs to excitatory and inhibitory population, and here where the limit cycle is, now the color coding is for number of spindles. This is very nice because that means that when our cortex is parameterized in a slow oscillation regime, meaning the cortex is doing slow oscillations, we connect it to the thalamus, so the cortex is driving the thalamus, then the thalamus is spindling. And as for the typical time series from this region, we could see something like this. And the plot on the right is very nice because we can see individual spindles, how they match up. So I did a spindle detection algorithm and then plotted around their peak. And we can see here spindles in white and the cortical slow oscillations in green. And what is very nice, it seems that the spindles are initiated on down to up transition in the slow oscillation and peak in the up state. And we also observe significant phase amplitude coupling, which is very nice because this is all qualitatively consistent with EEG data. I'm running out of time, so just very briefly, when we do the full model like this, we can change the connections from both ways, the feed forward from cortex to thalamus and feedback from thalamus to cortex, and we can see how the dynamic landscape of individual modes changes upon this connection, which is very important. And the final slide, this is how the typical time series looks like in the whole thalamocortical loop. And what is beautiful is that some of the thalamic spindles here in the blue are imprinted to the cortex, which can also be seen here in the time frequency representation. So the cortex is still doing slow oscillations, but we are also seeing some imprinted spindles. And very quickly to conclusions, we have successfully connected 2 sleeping brain modules. And we have modeled spindles and slow oscillation interactions and their cross-frequency coupling. And it seemed to be qualitatively consistent with the EEG data. And as for the next steps, we want to see whether these conclusions would carry over to the network level, which means we want to have more cortical nodes as per structural connectivity from the DTI, and then thalamus connected and see how this would look like. Some references and acknowledgements, and thanks very much for your attention.
Thank you very much, Nikola. You did take those 5 minutes quite literally, but we still do have time for discussion. I haven't seen any questions come in so far, so I'll give people a bit of a moment to kind of read through your conclusions again. Oh, someone's lifting their hand. Douglas, I've allowed you to talk if you wanted to ask a question.
Hi, can you hear me?
Yes.
Yes.
Hi, yeah, thanks, great talk. I was just wondering, when you measure like the incidence of spindles or slow oscillations, are these just like in a sort of in a background state, or are these like connected to what you said at the beginning of the talk related to like how these oscillations are actually some kind of replay of memories?
Well, in our model is very, very simple. It's just phenomenological. So of course we do not have real memories encoded in our model in any way. I mean, the main motivation stems from the fact that if you want to do the memory consolidation, it is a very delicate process and you need a precise timing. So it is thought that the interaction of these oscillations, the slow oscillation and spindles, are not really connected or are not conveying the actual information transfer. It's more like they are setting a stage, if you will. They provide like a clock, like a temporal windows in which the hippocampus is said, okay, now the brain is very plastic in the up state, of course, because you have a lot of firing in the cortex. So now the brain is plastic, so you can start your memory replay. And the actual memory replay has nothing to do with slow oscillation of spindles. It's a very convenient to do the memory replay then. So we are not really modeling the memory consolidation by itself. We are just modeling the interactions and how they look like and whether they agree with the observed interactions in the EEG data.
All right, thanks. Yeah, it's interesting to see that you can like sort of do this coupling regardless of any memory. Yeah.
Yes, it has been also observed that even the thalamic slices, so you have thalamus completely out of your brain, and the thalamic slices are doing spindles by themselves. And also the cortex is doing slow oscillations by itself. It's just when you connect them, they start to be nested, and you have some hierarchical coupling between them, which is really nice, actually.
Yeah, yeah. So that's how I would usually think. Like I know of some papers where they sort of decouple these two, right? And then they show that this does not alter the frequency or the incidence of slow oscillation or spindles, but it just affects the coupling, right? I guess that's where you're going.
Yeah, exactly,
Right.
exactly. And as I was talking, the secondary motivation is that if you introduce the electrical stimulation to the brain while you are sleeping, you can actually play with this strength of this interaction. And by that, you can strengthen the memory consolidation just by playing with the strength of interaction between slow oscillation and spindles.
All right. Yeah, great. Thank you.
Thank you. Were there any other questions? And yeah, by the way, do feel free to just put your hand up as well. Like your virtual hand, and then we can help you to ask your question.
I had a small question. So,
yes, please go ahead. Yeah.
How easy would it be to incorporate other regions in this, like hippocampus, or do you envisage that it would be easy to capture that interaction as well in the same type of modeling framework, or do you envisage any difficulty?
Yes, that's a very good question, because ultimately that's when I hope where this is all leading to. The thing is that formally, I mean, just writing the code and integrating and simulating this, it's kind of easy, I need to say. I mean, it's like 1 or 2 days, yeah? But the problem is, of course, you need to do like the full investigation, what is actually happening there. And that is extremely hard because you have so many parameters. Fortunately, both of our models are very biophysically realistic, meaning that a lot of parameters are actually biophysical, so you can get the numbers for them from the literature, right? But still, you need to do a lot of investigation. So what we are thinking of doing is the next step is really to do like full cortex plus thalamus, and we need to see whether the slow oscillations would be doing waves, because in real brain the slow oscillations are actually waves traveling from anterior parts of the brain to the posterior. And the thing is, we are not really sure whether this will hold in our model well when we connect it with the thalamus, and just then there would be a nice window to try to add some good model of hippocampus. Another problem is that usually when I was checking out some hippocampal models, you either have spiking neuron models, which won't work with our population-based models, and the population-based models of hippocampus, I haven't seen not one. So this would be more problematic because even the model of hippocampus is not readily available. So that would be really challenging.
Thank you.
Thank you. There's one more question in the Q&A. Sorry if I mispronounced your name, Aishwarya. I've unmuted you, so you'd be able to ask this question yourself if you want. So the question is, can we also look at interactions in terms of spindles and wakefulness using these models? Brief answer, please.
Yes, spindles and wakefulness, yes, that might be possible. I mean, from the parameters I put into my models, the model is parameterized such that it is sleeping brain. But of course, changing some parameters, in particular, for example, the there are this neuromodulation via acetylcholine, which is thought that this is something like waking up from the sleep. So upon changing some of the parameters, you can model this. The whole model would be as if you are not sleeping, but awake. The problem is when you are awake, we cannot see slow oscillations at all, because then the main activity is fast, right? It's like alpha or beta. Only if you are sleeping, it's very slow, like slow oscillations. So you can still maybe see spindles, but not slow oscillations. Therefore, it doesn't really make sense to study slow oscillation and spindles interaction in the awake brain, because there are none.
All right, thank you very much, Nikola. This leads us just on time to our next speaker.